All right, so as I said, today we're starting with convection. All right, so convection it's really similar to conduction in some ways because what we're talking about now instead of say two bodies where you have heat flowing from one body to the other body and just through conduction, you have now one of the two sides of this system is moving, right? But the mechanisms of heat transfer from the surface into the moving fluid is still conduction, right? So we still have a conduction problem. It's just that one of the things is moving now, and we have to go through the analysis that deals with that. So today we're going to just go through and kind of introduce a lot of thought processes around the boundary layer. Right, the boundary layer is the region that we really care about. So we have this body that's fixed, and we have fluid moving over it. And the entire behavior associated with that body or with that heat transfer process is really governed by what's happening in that boundary layer, that thin layer right next to the surface. Okay, so we are going to go through and kind of explore that a little bit. So let's start off here. So boundary layer concept. So let's sketch out a boundary layer. So let's say we've got some plate. Sorry, is this mic a little loud today? Let me turn it down. You can hear the echo. Okay. So we have some surface, right? This surface is out in space, and coming into this surface, we've got some fluid. This fluid is moving, and it's moving because we're applying some, I don't know, say there's a fan blowing it over the surface, there's a pump moving the fluid or whatever it is. It's moving by some external force. Okay, we'll say this exists at U infinity and T infinity, right? These are the velocity of the fluid and the temperature of the fluid coming in. And then let's say that there's a coordinate system here. We've got coordinate X and we've got coordinate Y. Okay, so if we think about what's happening here, just in terms of the velocity profile. So let's pick some location, I don't know, here. And let's sketch the velocity profile at this location. Right? What is the velocity profile going to look like? We've had a chance for the fluid to already move past the leading edge of the plate. But what is true at this? So if we sort of plot, this is our velocity coordinate here. So what is true of the velocity right at the surface? It's zero, right? It has to be zero. So we have a no slip condition here at the surface. Okay, so velocity there is zero, and what's true of the velocity way out, far away from the plate? It's U infinity, right? So we could draw that. Let's say pick a point out here. So this will be our U infinity coordinate. So that's true, right? And now we connect the two in this way. So we'll sketch the curve between these, and it's going to look something like this. So now the velocity profile as a function of y looks something like this. So we can say it looks like this. All right, this position here, right, this kind of dot that I drew, that is, let's say, about equal to U infinity. It's not exactly equal to U infinity, but it's really close. And the width of this layer is called the boundary layer, right? The boundary layer thickness. So we'll call that delta. Okay, so this delta is what we're going to call our boundary layer thickness, and this particular boundary layer is the momentum boundary layer. Let's write this out. This is the momentum boundary layer, which I'll periodically abbreviate BL, boundary layer. And it's called the momentum boundary layer because it's the area of the fluid or the region of the fluid that's affected. Its momentum is affected by the presence of this surface. Okay, so we usually give this delta M. So delta M is our momentum boundary layer. Okay, so this is generally how the behavior of a boundary layer looks when you have the velocity considerations. Now let's look at the same thing happening, but for temperature. So let's say we have, again, some surface, and this surface is now being held at T sub S. Some surface temperature T sub S, and T sub S is greater than T infinity. So you have heat transfer away from the plate. So let's pick a position here. Okay, there. And let's sketch the temperature profile here. The temperature profile is going to be, let's see, I'll draw it in red. So let's say here, right, this plate is going to be at TS. This is our temperature TS here. As you move away from the plate, what's the temperature going to be if you get far enough out? It's going to be T infinity again. So if we get far enough out, we're going to have T infinity. We'll say this is T infinity. And you sketch those two things, connect them together, and the boundary layer looks something like this. All right, so we have, now instead of no slip, we have a forced temperature or a fixed temperature at the surface. As you move away from the plate, the temperature returns to T infinity. At some point, you're close enough to T infinity that you say, this is effectively the region that's been disturbed by the presence of this plate, by this the TS being here, right? Now let's see if there's anything else. So yeah, let's label this, right? So this thickness here, right, this thickness here is called delta T. This is the thermal boundary layer thickness. All right, now let's move down the plate a little bit. So let's go down further in the direction X, and let's do this again. All right. Now, if I draw this again, I still have out here, I've got my TS, right? This TS is the same TS as it was before. We're holding that temperature constant. So what's going to change about this problem as I move further down the plate? Think about what's changing as I move further down the plate. Well, I've had now time for this surface to affect the region around it. The further down the plate I go, the more time effectively that the fluid has had exposed to this surface. So the bigger the boundary layer is going to be, right? It's going to continue to grow as you move down the surface. So now I would say my T infinity might be somewhere out here, right? And if I sketch it, it might look something like this. Right? So this is TS here, this is T infinity. So now my thermal boundary layer thickness is this, delta sub T. Right? So if I sketch this, thickness of the boundary layer is a function of position. It's going to start off right at the leading edge. It's going to start off at 0. There's 0 thickness. If I sketch it, it's going to look something like this. Right? So you have this thermal boundary layer that right at the leading edge is immediately starting to grow. And then as you go further and further out, it continues to grow. All right, we've seen this before. We've seen this problem before, just not in the context of moving fluid. So where have we seen this exact behavior before? Not yet. We're not internal flow. In a conduction problem, we've seen it before, right? We've seen it in a conduction problem, yeah. We've seen it sort of. So we've seen it where you have transient conduction in 1D. Right? So this is effectively the same thing as I take a boundary, at time equals 0, I raise the temperature of the boundary and you see this thermal wave propagate into 1D. It's exactly the same thing here, right? This is exactly the same, except that we just have one thing that's moving now. Right? So then what is our, what's our component of time? Well, our component of time has to do with the velocity of the fluid and the length along the plate. Okay, so we'll kind of get into defining that a little bit better as we go. Okay, so let's just get some things here clear. So we have U is our velocity in the X direction. We're going to introduce V. So V is our velocity in the Y direction. All right, for a problem like this, we don't really have any V velocity. You have a fluid coming in and it's shearing over itself, right? The stuff right on the wall is not really moving. So you get away from the wall, it's moving more quickly. There's really not very significant velocity in the Y direction. There has to be some due to conservation of mass, but there's really not that much there. So the V component of velocity for laminar flow, this is laminar flow over, we'll talk about what that is, but laminar flow over a plate is really, really small. So for problems like this, we're mostly just talking about U velocity, okay? Okay, so let's, one other point. So I've kind of drawn this where this wall is, or this, this boundary layer is growing. So when we're talking about problems like this, where the boundary layer continues to grow, the question is, will this boundary layer ever stop growing? Will it ever stop growing? Will a 1D conduction problem ever stop conducting in a semi-infinite body? No, it's always going to continue to grow. So as long as you have laminar flow, the behavior is going to look like this. It's going to always continue to grow indefinitely. Okay, so if we have a situation where, let's say I had a wall here, right? Some kind of a wall that eventually the boundary layer grew into that wall. In that case, then it's internal flow, right? So if you have some wall, this becomes internal. And it's only internal as much as it's interacting with another surface as the boundary layer grows. If it never interacts with another surface, we consider that external flow. Okay. So external flow is a flow that's unaffected by another surface. Right, so it's flow where the boundary layer is unaffected by another surface. Let's say boundary layer. Right. Any questions on this so far? It's pretty conceptual stuff. Okay. Oh, so what this is saying is it's a little confusing. So if I plot, I'm introducing a new plot where this is t, like this coordinate is t. So I'm saying here this on this coordinate system would be ts, and this would be t infinity over here. So it's just saying like it's starting off at ts near the wall, and then as you get away from the wall, you go down to t infinity, and you continue indefinitely off into, indefinite length at t infinity. It's not like the temperature is going up. It's just sort of the plots like this. Yeah. Yes. Yep. In the free stream. Yep. So you hear the words like free stream. It's the same thing as the infinity we're putting in there. So if you go off to infinity, that's the free stream.